Project number 3, Inferential Statistics. To begin, go to your Statistics Projects file and go to the third sheet titled Inferential Statistics. We can move this information out of the way. Okay, let's we can go to our Statistics Projects Templates file and scroll down to the beginning of the third project to see what the first page should look like. So we need the executive variables, salary, gender, pay, payee, and salary 2. First though, let's change the orientation to landscape. We should change the column width of A to 17 and B through L 9. Alright, we can put a spanning header up here, data. Bold it and put some color behind it. Alright, now we can go to our first project and grab all the data. Right click, copy, and paste it. Good. Now we only need salary, gender, pay, and a new variable, 2 new variables, payee and pay. So let's get rid of age. We can just take this block, move it over, and take this block and move it over, and then call this payee. Now payee is just like pay. Recall that for pay we had high if salary was greater than or equal to 86, or else low. So for payee, instead of quotes high and quotes low, we want just simply 1 and 0 without the quotes. So go over here, we can say equal if, left parentheses, grab the first salary. If this one's greater than or equal to 86, and it just happens to be equal to 86, that's coincidence, we want to say 1, comma 0, like that, and then we can take that, double click it down. Excellent. So note that payee is 1 every time pay is high, and payee is 0 every time pay is low. Now we can take our salary 2 variable that was originally in the file, on the sheet, take it over, and there. We have our data. Now notice that the data goes beyond the first page, so we can grab row 4 through 38. We can right click, say row height 13.5. Alright, now it's on one page. Also, we can create a few named ranges. We actually need 3 for this project. We need the entire set of data with the labels. So grab all that, right click, say define name. We're going to call it data, and scope it to the third sheet, Inferential Statistics. That way when we use the named range data, it only refers to this sheet, and it will only be able we will only be able to use it in this sheet. Okay, and then we also want to do salary that way. So right click, define name, salary, scope it to Inferential Statistics. Do the same thing for payee. You can actually hit Control Shift arrow down, right click, define name, payee, scope it to Inferential Statistics, and then we can open up the name range box to verify that indeed our named ranges are in there, and they are. Great. Now if you make a mistake with the named range, recall that you have to go to Formulas, Name Manager, and you can sort them by the scope, and you can just delete. Usually it's easiest if you made a mistake on a named range just to delete it and start over. Right? Now for the second page, we can look at our statistics project templates file and see that we need to type in some information here. Let's start with the top. This is what I call the work section. There's a work section for salary, and then there's a work section for pay. We're going to be analyzing salary and pay. Salary is a normal random variable, and pay is a Bernoulli random variable. So let's type in, or begin to type in this first section here. So we can start with the spanning header. We can say, actually we can go up and grab our data spanning header, Control C, and Control V. Actually I want it right underneath there, and call this salary. And then we can skip a row and start with the description that says variable, colon, and we want to say salary, which is assumed to be normal. All right. Now make sure it's just left justified, and you can let the words just spill over into the adjacent cells. No need to merge it in center or anything. Just keep it left justified. Now I can bold the variable in the colon. Good. So continue to type the top portion of the information in here, and then we can start with the formulas. Okay, in order to fill in the results here for the work section, go to our statistics projects templates file and the formula sheet at the back. And we see the formulas that we need. Now there are two sheets for the normal analysis of salary, and there are going to be two sheets for the Bernoulli analysis. We actually need just the first sheet here for the work section, and here are the formulas. We note that subscript 1 refers to males and subscript 2 refers to females. Okay, so let's do a few analyses here. Now I want to show you a special function coming up, but first let's do some statistics that are relevant for the one population analysis of all executives. So what's the formula for the mean? Well, this is the average function, right? So we say equal average, and we can type in our named range salary. All right, and we can center with 3 decimals. Now over here we want to calculate the average for males, the average salary for males, and then following next to that we want the average salary for females. So we can use a database function to do that. The database functions are the same as the regular function except for you put a D in front of it. So here, if we want to calculate the average salary value for all males in the gender column, we can say equal D average, and then we can write in data. That was our named range data, and the field is salary. We need to put that in quotes. And then the criterion is all the males in the gender column. So we can grab these two like this. Good. And then we can use 3 decimals. Make sure it doesn't say general up here in the name format, and center it, and we can actually drag it across. Excellent. So notice that the gender male turned to gender female. We still have our database data, and the field is salary. Okay, you can go ahead and fill in those formulas right here. Note that when you do the special degrees of freedom, first you're going to get 29.008 and use the round function with 0 digits. Okay, here are the results of the salary work section. Next, we can begin with the confidence intervals for salary. So we need to type in this information here on the second portion of this page. So let's begin that. We can take this header here, skip one row, and then type in confidence intervals. And then we have one population. We can center that and put some color behind it and bold it. And we can do the rest according to the templates package. Okay, here's the shell for the confidence intervals. Note that there's for the two population analyses, both unequal variances and equal variances, there's a delta means here. To get the delta, you go to Insert, Symbol, and in the subset in the upper right hand corner, you can go to Greek and Coptic, and you'll see a delta there. Okay, that's the delta we want to use. So put that in there. Now, note that for each of the three analyses, the degrees of freedom will change. So will the standard error. Now, we've calculated them up above in the work section, and note that they're in the order in which they appear. So here's the first degree of freedom. It's appropriate for the one population analysis. Second degree of freedom, special DF, is appropriate for the two population unequal variances, and the third degree of degrees of freedom is appropriate for the two population equal variances. Note also that within each of the three, we're using the three confidence levels of 90%, 95, and 99, which correspond to alphas of 0.1, 0.05, and 0.01. Okay, so let me show you how this can be done. We can say equal, grab the first DF. We're going to lock it because I'm thinking ahead. I want to do some copying. And let's center this and use 0 decimals. Now the mean is the overall mean, so we grab that, lock it as well. Let's center it and use 3 decimals. Standard error is the first standard error, which is the 1.514. We'll lock that. Again, center it. Now the critical T, we have to get that using an Excel function. So we'll go to our formula sheet again. This is actually on the second page for the salary, second formula sheet for salary. Right there, and we see that the appropriate function, or the function we need, is t.inv with 1 minus alpha over 2 and the degrees of freedom. So we grab it from the same row. We'll say equal t.inv, left parentheses, grab, say 1 minus alpha over 2. Do not lock the alpha because we're going to want to be able to copy it. And now we need to grab the df, right like that. Good. Now we can, for the rest of these here, we can center all at once and use 3 decimals. So that anything we type will have 3. And the margin of error is the standard error times the critical T, or the critical T times the standard error, either way. So we'll say equal, grab the critical T times the standard error. And then the lower CL is the mean minus the margin of error. And the upper CL equals the mean plus the margin of error. Good. Now we can drag this down. And it works fine. Now, let me show you here, or note that as the confidence goes up, the width or precision of the confidence interval goes down. Precision goes down, or the width gets larger, right? Right, the numbers get spread further and further apart as you get more confident, so we lose precision. All right, let me show you how quickly this can go. The second degree of freedom is the special DF. This is the DF appropriate for two population unequal variances. So we grab that, lock it, and now delta means is what we need for our all two population analysis. So we'll grab our difference in means up here, lock that. Now I can do the center and 3 decimals. And the standard error now is the second standard error in our second column, or first standard error in the second column, F4. Critical T again is equal, actually we don't need to copy that, copy these down, or we don't need to type that in. Now what we can do is take this whole section here, Control C, and then Control V, and nice, now we have our confidence intervals for two population. So the interpretation of the first confidence interval, we can say we are 90% confident that the population mean salary for business executives in Ventura County is between $84,812,000 and $89,931,000. For the two population analysis, we can say we are 90% confident, the first one here, that the population difference in the means of the male salary and the female salary is 8.296. Sorry, we are 90% confident that the population mean difference between the males and females is between $3.584 and $13.008 thousand. Okay, here are the results of the confidence interval section for salary. Next we can begin the hypothesis testing section. So this is hypothesis tests. Right, now we want to again identify one population. And then we're going to actually merge and center this one piece here. All right, and underline it. And then we can type the rest of this in here. Okay, here's the shell for the first two hypothesis testing sections, the one population and the two population unequal variances. Note that here I've got a Greek letter mu with a space and then a greater than or equal to sign. You can get those once again from the insert symbol. The greater than or equal to and the less than or equal to are part of the recently used symbols when you first pull it up, and the Greek letter mu again comes from, if you change your subset in the upper right hand corner to Greek and Coptic, you will see the mu. Where is it? Right there. There's the mu. Also note that here we have some subscripts in here. Let me show you the best way to do this. You can insert the symbol mu, actually type the entire where's the Greek and Coptic? There it is. Type in the mu and the capital M space minus space and then mu, we can just copy and paste this, capital F space and then insert the greater than or equal to sign. Do it all at once first. We can italicize the mu's, both of them. And now we can grab the M, right click, say format cell, and turn that into a subscript. And then do the same thing with the F, format cell, subscript. All right. And then of course you can copy and paste that and change the greater than or equal sign to equal, less than or equal to sign, and then an equal sign. And once you get one block of 3, you can just copy it down. Now sometimes the row height will change when you put subscripts in there. So what you can do is right click on any row, say row height, and then bring it back to 15 if it did in fact change. Now note also here that we have these green values here. These are the values that are flexible in the analysis. They're the ones that were gotten from the original information that I provided. So the one population hypothesis testing for salary will be 90, the value, and then for both two population analyses we'll be using 2. And then for the pay analysis of Bernoulli variable, we'll be using 0.3 for the one population analysis and 0.1 and 0 for the two population unequal and two populations equal variances respectively. Okay, let's see how to fill in these formulas now. Once again, for the analyses, the degrees of freedom will change. So the first degree of freedom is appropriate for the one population analysis, so we can take that. As a matter of fact, we can take the mean degrees of freedom, the mean, and the standard error, and pop it down there. And then the 29 will be appropriate for the second one, and we'll copy more down later. So 34 will be the whole first section here, 29 will be the whole second section, and so forth. 33 will be the appropriate degrees of freedom for the two population equal variances. Okay, so now the t statistic, if you go back to your formula sheet, the t statistic is the sample mean for one population, or the delta means when you're working with two populations, minus the hypothesized value divided by the standard error. So we have here equals, grab the mean minus the hypothesized value, enclosed in parentheses there, divided by the standard error. All right, we can center that in 3 decimals. Drag it down. Note that the dollar sign is locked on the DF mean and the SE because we had the dollar signs above before we copied. No dollar signs for the t statistic. Now the lower critical value and the upper and the lower and upper for Form C. Form A is a left tail test, so there's going to be a lower critical value, no upper critical value. Form B right here is a upper tail test, so we'll have an upper critical value, and Form C is a two tail, so we'll have a lower and an upper tail, lower and an upper critical value. Now notice that for each of these analyses, I've changed the alpha again, 0.1, 0.05, and 0.01, but we've done all 3 forms of the hypothesis test, A, B, and C, A, B, and C, and so forth. All right, so now the lower critical value here is using the t-inverse function again, so we say equal t dot inv, left parentheses, and we use the alpha and the df, so grab the alpha from the same row, comma df, no dollar signs, good. And again, we can, all 3 of these we can, and this one will be the same thing, but 1 minus t dot inv, left parentheses, 1 minus alpha, comma df. Good, and this is then alpha over 2. So we can actually drag this down, get rid of this here, and then put in an alpha over 2, and then drag this down, put in there 1 minus alpha over 2. Now, note that once you get your p-values in, and the p-value formulas come from the sheet over here, there's one for Form A, one for Form B, one for Form C, and you do your decision using an if statement. You can copy the entire block down like this, and everything will automatically adjust. And if you want to then do the two population analysis, once you've filled in your degrees of freedom, your delta means, and your new standard error, we can take this whole block here, Control C, Control V, and copy that down like that. Great. You can do the same thing then with the third section as well. Here then are the results of the salary hypothesis tests. Now for the equivalent to population hypothesis test, we want to get Excel to automatically do the analyses for both two populations types of analyses, unequal variances and equal variances. So in order to do that, the data has to be in columns. So we need I span a couple cells here, and I put male and female, and then I go up to my data, and I grab all the data, and I go to data, sort, and then I sort by gender. Now I have all the female and male salaries next to each other, so I can right click, copy, paste the male values there, and then I can go up and do the same thing, grab my female values, and then I paste them there. Now I'm going to go ahead and unsort. Now make sure that you grab the same amount of columns when you unsort that you grabbed when you sorted. Personally, I grab all the data when I sort, and that way I know that when I want to unsort, I just have to grab all the data once again. So I can go back up to data, sort, executive now, and it gets the data back to where it was before. Good, and I still have my values down here. Now, let's go to data, data analysis. Now recall, if data analysis does not show up, go to File, Options, Add-ins, try it again. Yeah, add-ins, go, and check the analysis toolpack box and OK, and it should show up. Okay, so go to data, data analysis. Down at the bottom, we have a t-test assuming unequal variances. So our variable input range is male, and with the label, grab the female salaries with the label. Now the hypothesized mean difference is the same one that we use, the green value that we've chosen for this first for our project here, so it's 2. We type in a 2, check labels, and in the output range, once in a circle, once in the open box now, and we click in upper left hand corner where we want the output to be, and there we go. Now we can center and use 3 decimals, and let's green and bold the value that's free to vary, and red and bold the t-statistic. And we can verify if we did things correctly. The 2.271 should match the t-statistic. It does. Note that the special degrees of freedom, 29, is automatically calculated in Excel. That's the 29 degrees of freedom that we calculated in our work section. And you get the same p-value, 0.015 and 0.031. There it is, 0.015 and 0.031, so we know we did it correctly. Okay, go ahead then and replicate the two population equal variance analysis. And then there's a third analysis down here, F-test two-sample for variances. What this is note that the difference between the two population unequal and two population equal, that the second one assumes the variances are equal. You may be interested in testing that, the null hypothesis that they are not equal. Test the null hypothesis that they are equal. And so you can do that using the data analysis tool. They're in alphabetical order. So here's the t-test assuming equal variances. That's the second one you're going to do. We did the first one, t-test, two sample assuming unequal variances. Then here's an f-test. Again, the null hypothesis is that the variances are equal. If you get a small p-value, you reject the null hypothesis that they're equal and conclude that they're unequal. And this test can help you determine which analysis is appropriate for you, the unequal variances analysis or the equal variances analysis. Finally, there's a test down here, a t-test paired two-sample for means. Unlike the first three analyses, which compare males versus females, this last test here, t-test paired two-sample for means, compares two salary values. We're going to do salary versus salary 2. Note that for each observation or each executive, there's a pair of values. So instead of comparing females versus males with respect to salary, we're going to compare salary across all males and females, the first salary, with salary 2. The null hypothesis is that there is no change. So we want to see if indeed there is a change between salary and salary 2. So we're using different columns for the final analysis, and we want to put the hypothesized value in there of 0. Okay, so go ahead and do those. We see that we failed to reject the null hypothesis that the variances are equal because the p-value is 0.208, and conclude that from this then you could conclude that the analysis assuming equal variances is appropriate. Also, we see here that we reject the null hypothesis that salary 2 is equal to salary, one-sided test because the p-value is 0.038, and we fail at 5% to reject the null hypothesis that salary 2 is either larger or smaller than salary. All right, so here's the pay section. Note the formula. There's a new formula sheet for pay, or Bernoulli. So here's the work section formulas. And then here are the confidence intervals and the formulas for that. Note that there's no two-population equal variance analysis for Bernoulli. That's because if the p for the male is different than the p for the female, then the variances will be different, because the variances for Bernoulli is p times 1 minus p. But note that the standard errors do follow the order, just like before. So for the one population analysis, there's the standard error. And for the two population analysis, use the second standard error right there. Now for hypothesis testing, there actually is 3 different sections, including the two population equal variances. That's because in the unique situation where for hypothesis test, when the hypothesized value is 0, that means you think that the p's, or you're testing that the p's are the same. So when you're doing a hypothesis test, you assume that the null hypothesis is true. So therefore the p for the males is equal to the p for the females. Therefore pm times 1 minus pm is equal to pf times 1 minus pf. And you can actually use a pooled variance in this analysis. So when you have the hypothesized difference of 0, there actually is a standard error based on the pool variance, like there was for the salary analysis. So that's that. Now there's one special section, one standard error that doesn't follow the pattern. this is the one population. If we were following the pattern, we would use 0.084 for the one population hypothesis test, but you see here it doesn't. The other two do follow the pattern. The two population unequal variances uses the 0.162, and then, like I said, the special case when the difference between the proportions is 0, there actually is a standard error based on the pool variance, so that's the third one up here. That's fine, but this one is different. So when you're doing a hypothesis test, you assume that the null hypothesis is true, so you're going to assume that your p is 0.30. So instead of basing the standard error on the sample values, you base the standard error on the null hypothesized value. So this is the formula that you're going to use. Same formula, but just a different value. So it's the square root of the 0.3 times 1 minus 0.3 divided by the count, the overall count, which is 35. So lock the 35, and then you can copy it down. Now, please bold this here because it's different. I want it to stand out. It doesn't follow the pattern. So all the other ones do. Okay, so here are your results of your confidence intervals and your hypothesis test. Okay, let's do the equivalent two population hypothesis tests. So just like for the salary, we want to get Excel to replicate both two population analyses, one for unequal variances and one for equal variances. Now we can do that using, again, the data analysis tool. This time we're going to use the z-test two sample fermions at the bottom. Okay, so once again we're going to have to get our data in columns, but this time instead of using salary, obviously we're going to use the pay-D, the ones and zeros. Again, you can sort your data by gender and then grab the zeros and ones when they're next to each other. Now make sure you do a paste special to get the numbers, otherwise the formulas will copy with it. Recall that we used formulas to create our pay-D variable. So the paste special, and when you paste just the values, then you won't paste the formulas and you won't get nonsense when you try to paste the formulas. So okay, the first variable then is male. Grab it with the label, and female. Now the hypothesized mean difference is the same one that we used above, so that we can get Excel to replicate the results, and that's going to be 0.1. Now this routine was actually designed for the situation for normal variables where the variances are known, but we're going to use it for the proportions analysis when the variances in fact aren't known, but we can use the sample variances in that place there. So this is why, if you noticed up here, I used 4 decimals for the male and female variance, and I also used 4 variances for the pooled, 4 decimals for the pooled variance. So we need that much accuracy so that our results will match up perfectly. So we're going to put in here 0.2148 for the male variance and 0.2438 for the female variance. And then we're going to click the labels and then output range, once in a circle, once in the open box, and we can put it right there, and there we go. Now we can center and use 3 decimals, and we can bold in green the value that's flexible that we chose, and then also make these 3 decimals, bold and green those because we put those in, and then red and bold the z statistic. And then we can see if the z statistic matches up to our analysis above 1.027. It does. Good, so we've done it right and done it correctly. Now go ahead and do the z-test 2 sample for means, but in the case where we have equal variances, recall that we pooled the variance to get the standard error. So you're going to use the 0.2482 for both male and female variances. And then you'll be able to replicate the analysis and you'll get a z statistic of 1.576. Finally, we can do a test of independence for gender versus pay, and you can do the education versus pay in the same manner. So let me show you how to do the gender pay analysis. So we'll go to Insert, Pivot Table, like this. And now recall that we're going to, when you do a pivot table, you grab all your data with the labels and hit OK. Now don't forget to go up to Options and make sure you uncheck the auto column widths on update. Otherwise, everything you type from here or anything you work with in a pivot table will alter the column widths that we fixed from the beginning. All right, let's put gender in the rows. Let's put pay in the columns. And then take executive, put it in the sum values, and change that sum to the, you can say value field settings and change it to count. We don't want to sum the executive IDs, we just want to count them. Okay, excellent. Now we can go in here, center what's on that portion of the table, change this column labels to gender, sorry, that's pay, and then down here will be gender. We can click out of here and go to design. Let's open up and use the very lightest one. Good. Now we can copy this portion of the table, Control C, skip a couple rows, Control V, and just create a shell. And we can clear this out. Clear these numbers out of here. Draw a shell like this, or the box. There we go. We can do 2 of them. Good, and then we can type in here observed frequencies. And we can red and bold that. And then down here, we type in expected frequencies. And now all these should be greater than or equal to 5. And again, we can insert a symbol, say greater than or equal to 5. Bold and red that. And then these are called the cell chi-squares. Actually, I do it this way. And bold and red that. Now, if gender and pay are independent, then the expected counts, or the frequencies, can be calculated by taking the row total, or the column total, times the row total divided by the grand total. So let's do it in here. Let's write a formula so that we can copy and paste it once. So we say equal, grab the row total, and thinking ahead here, we want to copy this down, and the 19 to move to 16, but we don't want, when we copy the formula over, the 19 to move to a blank. So we want to freeze the letter, if you will. So we can say F4, 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 freezes just the letter. Now, multiplied by the column total. And now this time we want to freeze the column, or the row, the number, but not the letter. So hit it twice, and now divided by the grand total of 35, and we want to lock both in the row and column direction. Okay. And let's use 1 decimal inside there. Now we can drag it down, drag it over, and we can make our box, clear everything, and then put a box on the outside. Okay, so these are the expected frequencies under the hypothesis that gender and female are independent. Now, so the difference between the expected frequency and the observed frequencies gives us an indication of how close or the degree of independence that we actually see. So let's do this. This is the observed minus the expected squared divided by the expected. So it's the observed minus the expected squared divided by the expected. Good. And let's use 3 decimals here. Actually, let's use 1 decimal. And again, we can clear out and put a box around it. Now, the chi-square statistic is the sum of the cell chi-squares. So the larger these are, the less likely there's independence. Okay, let's center that and use 3 decimals. Now the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. So we can say equal rows of this thing minus 1 star. We better put a parentheses in front there. It's the rows. Yeah, no, row is right. Rows. Rows times parentheses columns. Of the same thing. Minus 1 and parentheses. Good. We get 1, use just 1 decimal. Or sorry, no decimals. And then we can use the chi-square.dist function to find out the probability in the upper tail beyond 2.485. So we grab the 2.485 as our x, comma, grab the degrees of freedom, and we say true. And we get we actually need 1 minus chi-dist, true, and there it is. So in this case, we fail to reject the null hypothesis of independence because the p-value is less than 0.05. All right, so go ahead and do the test of independence for education and pay. And that completes project number 3.